Welcome to the Deep Dive. We're the show where we tackle some pretty complex stuff, grab the research, and really try to break it down into what matters most, maybe find those mind-blowing insights. Today, we're embarking on a deep dive into something truly extraordinary, something many of us take for granted every single day: the human hand. I mean, just think about its dexterity for a second. It's almost magical, isn't it? How it can delicately pick up, say, a feather with such incredible precision. And then, literally, the next moment, it can grip a heavy hammer with, like, immense force. And you're not consciously thinking about every single muscle, every tendon, every joint involved. It's just the seamless symphony of action. But then, pause for a moment, try to wrap your head around the sheer engineering challenge of trying to replicate that dexterity in a robot. It's one of the big goals, maybe a holy grail in modern robotics, and it has proven surprisingly incredibly difficult. For decades, engineers have been trying, really struggling to create artificial hands that can match even a fraction of what our own hands can do, their versatility, their adaptability. So this isn't just about building another robot hand, it's more about fundamentally rethinking how we control these really complex machines, maybe aiming for sophistication through, believe it or not, simplicity. Okay, so let's unpack this properly. We're diving deep into something called the Marionette Paradox. It's a really groundbreaking thesis that offers a remarkably elegant solution to this exact problem: robotic hand control. The paradox itself is kind of intriguing. How do you get these complex, high-dimensional movements from controls that are surprisingly simple, low-dimensional?
Yeah, and what's truly fascinating here, I think, is how this work manages to bridge disciplines that you might not normally connect. It draws inspiration from, well, classic puppetry, believe it or not, but also from the really intricate details of human biology, how our hands actually work, and then combines that with cutting-edge machine learning. So our mission today really is to thoroughly understand the full system architecture of this proposed robotic hand. We're going to put a sharp focus on two absolutely critical components, something called the synergy matrix and manifold learning. And we'll explore how these two elements working together fundamentally reduce the number of actuators the motor's needed. You'll see how a design that looks perhaps deceptively simple can achieve really quite sophisticated movements. It's a kind of unexpected elegance, you know?
Right, an elegance born from constraint, maybe. So to really appreciate the genius behind the marionette paradox, we first need to understand the scale of the problem itself. Why are robotic hands so notoriously difficult to build and control? You might think, sort of intuitively, that to make a robot hand as good as a human one, well, you just stick a motor on every single joint. Makes sense, doesn't it? More joints, more motors, gives you more control. But here's where it gets really counterintuitive and pretty challenging. Traditional robotic hands, they often demand this direct one-to-one mapping between the actuators, those motors making things move, and the degrees of freedom, which are essentially just the different ways each joint can move. So if your hand has, say, 20 plus distinct joints, maybe even more, you're suddenly looking at needing 20 plus individual motors. And each one needs its own complex wiring, its own control signal. It gets complicated fast.
Exactly. And this approach, I mean, theoretically, it offers the maximum possible independent control over every single joint, right? But in practice, it leads to some really significant challenges that have, frankly, plagued robotics for a long time. First off, you've got the high hardware costs. We're talking about needing lots of specialized, often custom-made miniature motors and really intricate mechanical linkages to connect everything. Then there's the huge energy consumption. Each one of those motors needs power, often all at the same time, which drains batteries quickly, generates a lot of heat inside the hand itself. It also significantly increases the hand's weight. And that's a major headache for robotic arms because payload capacity is always limited. A heavy hand means the arm can lift less. And maybe the most critical part is the control overhead this creates. It's a computational nightmare, really. The robot's brain has to constantly calculate and coordinate the precise movements of dozens of independent motors, often in real time, just for a simple grasp. So that makes the system computationally very expensive. You need powerful processors, complex control algorithms running constantly. And furthermore, and this is a huge one for actually using these things in the real world, it makes them highly prone to mechanical failure. The more moving parts you have, the more wires, the more components, the more things can break. Research, going back years and even recent reports like the NASA RAP report, they consistently highlight how this complexity often compromises speed, adaptability, especially in dynamic situations, and even fault tolerance. You don't want things failing in critical environments like space or hazardous waste cleanup. So yeah, this conventional approach, it seems direct, but it becomes this massive bottleneck. It hinders practical, robust, cost-effective deployment of truly versatile robotic hands. It's a tough engineering hurdle.
It really sounds like a case where just throwing more hardware at it, more motors, actually creates even more problems down the line. Complexity breeding complexity. But the human hand, by contrast, it's just this marvel of natural design, isn't it? It's actually what roboticists call underactuated, which sounds technical, but it's a beautiful, elegant idea. It basically means it has far more degrees of freedom, ways it can move, than it has directly independent muscle controls. Yet, somehow, it achieves all these incredible feats we talked about, the dexterity, the adaptability. How does it manage?
Well, it manages it through this really elegant coordination of several biological features working together. First, you have passive structures, things like ligaments, cartilage, even just the natural elasticity of the muscles. These provide compliance, a kind of softness, and they also help limit movements that aren't needed. Second, and this is really key for our discussion today, is the ingenious routing of tendon-driven linkages. Many muscles don't just pull on one bone, they act on multiple joints at the same time. And tendons often cross several joints, which creates these inherent coordinated movements almost automatically. And then, crucially, there's learned neural control. Our brains, they aren't consciously micromanaging every single muscle fiber or trying to calculate every joint angle in real time. No way. Instead, our brains learn these higher-level coordinated patterns of movement synergies, as we'll call them. It's this beautiful interplay between the mechanics and the learned control that allows for incredible dexterity with a surprisingly efficient control scheme, which naturally raises a really important question for roboticists. If humans don't explicitly control every joint independently, if our brains use these clever biological shortcuts and coordinated patterns, then why should we force robots into that computationally expensive, mechanically complex brute force approach? This biological insight, it's fundamentally pushed the field towards exploring solutions that reduce mechanical complexity right from the start. Instead of just adding more motors for every joint, the focus has shifted. It's shifted towards achieving what's called emergent coordination and exploring designs that are synergy-driven or use things like string actuation, like our Marionette example. The goal really is to let the mechanical system itself do some of the heavy lifting in terms of coordination, rather than trying to manage all that complexity and potential failure points with dozens of individual motors and really elaborate software. The shift towards implicit adaptable coordination.
And this is exactly where that marionette inspiration slots in so perfectly. It provides a truly elegant mechanical solution. Just picture it. A simple puppet, right? Controlled by just a few strings. But it can perform incredibly expressive, complex movements, a graceful dance, a dramatic gesture. Each string isn't just yanking on one isolated joint, it's transmitting motion to multiple degrees of freedom simultaneously. It creates coordinated, fluid actions naturally. And this idea lines up perfectly with the concept of under-actuated systems in robotics achieving complex movement with fewer direct controls. It's like getting more bang for your buck, mechanically speaking. Sophisticated motion without needing a motor at every single joint. It's almost like an ancient art form inspiring a very modern engineering solution.
Exactly. And happening at the same time, almost in parallel, and this is where the computational genius really comes in. We've seen these huge breakthroughs in machine learning, particularly in techniques for dimensionality reduction. Now, these advances are critical because they let robots move beyond just rigid pre-programmed movements or trying to calculate everything explicitly with inverse kinematics, which is computationally very heavy. Instead, robots can now learn these low-dimensional manifolds. You can think of a manifold as a kind of simplified map, maybe a curved surface, hidden within the much larger space of all possible movements. Imagine watching someone perform a complex task, like tying a knot. Their hand moves in incredibly complex ways, right? Lots of joints changing angles constantly. But the useful, meaningful part of that motion might actually lie on a much simpler underlying pattern or surface. Machine learning lets us discover and represent these compressed, simplified patterns directly from watching human demonstrations. So when the robot operates on this learned manifold, it's like it's navigating this simplified map where each point represents an entire complex hand posture or gesture. This allows for fluid, adaptive motion without needing to pre-program every single joint angle for every possible situation. It's a huge shift from explicit control to learned, implicit coordination, and it dramatically simplifies the control problem itself.
So, bringing this all together for our deep dive today, what does it all mean? The core motivation, the driving force behind the Marionette Paradox thesis, seems to be this ingenious combination of three powerful but often separate domains. First, that mechanical simplicity you get from the Marionette-inspired actuation. Second, drawing deep biological insight from how our own fingers coordinate forces those synergies. And third, leveraging these powerful learned control strategies using those manifold representations of motion. It's really about merging mechanical elegance with biological wisdom and cutting-edge computational intelligence.
Precisely. And the central question that guides this whole work is truly innovative, and it really captures the essence of the paradox. Can a marionette-inspired robotic hand, informed by human force synergies and trained on low-dimensional motion manifolds, perform expressive and adaptive manipulation using a reduced set of actuators? Now, this isn't just some academic thought experiment. A yes answer to this question promises expressive, low-energy, and highly adaptable manipulation for these under-actuated hands. It could open doors to more practical, more affordable, and more widely deployable robotic systems in the real world. It directly challenges that old assumption that mechanical complexity must be met with even greater computational complexity. Instead, it suggests that maybe true intelligence, true elegance, lies in finding those clever shortcuts, leveraging nature's own blueprints for efficiency.
Okay, so this deep dive reveals a really brilliantly structured system then. It's organized into these three distinct but interlocking layers. Each one builds on the previous one to deliver this sophisticated control, but with remarkable simplicity. You can almost picture it like a stack, right? At the bottom, the foundation, you have the mechanical layer. Then comes the coordination layer. And right at the top, bringing it all together, the control layer. Each layer has its job, but they all work together in harmony.
Yeah, and connecting this back to the bigger picture, this layered approach is absolutely fundamental to achieving that high dexterity without the traditional complexity. It cleverly breaks down this really daunting problem of controlling a complex hand into these manageable, biologically plausible, and importantly, computationally efficient parts. By clearly separating the physical design, the mechanics from the coordination logic, and then separating that from the higher level control intelligence, the whole system gains this wonderful modularity. It makes it easier to design, easier to test, easier to troubleshoot, and it gives you tremendous flexibility too. For example, you could potentially upgrade the control algorithm, the top layer, without having to completely redesign the physical hand underneath. It's really just sound engineering, breaking a complex problem into simpler, interacting parts applied beautifully to robotics. It leads to a much more robust and scalable solution overall.
Right. Let's start at the foundation then, the mechanical layer. This is the physical hand itself, and this is where that marionette design really comes into play. The hand is actuated using tension strings, just like a puppet. These strings are cleverly routed over tiny pulleys, maybe through some springs for compliance and through the hand's joints. But here's the really crucial part, the key difference. These strings, they don't originate from motors that are embedded inside the fingers or even in the palm. That's the traditional way, right? Which takes up a lot of space and adds weight. Instead, they originate from an external control board. This board is located completely off the hand, maybe in the robot's forearm or even further away. Then these strings run down and terminate at specific points within the fingers, effectively simulating how tendons work in our hands, pulling on the bones to create movement.
Exactly. And this specific design choice, the marionette mechanics with those external actuators, is absolutely fundamental to reducing the actuator complexity and, critically, the overall weight and bulk of the hand itself. Because the motors aren't jammed into the fingers of the palm structure, the hand itself is inherently much, much lighter and far more compact. This externalization dramatically cuts down on the physical space needed within the hand, allowing for a more slender, maybe even more human-like shape. The system is intentionally designed to be under-actuated, fewer motors than degrees of freedom. This inherently slashes the hardware costs and complexity compared to those traditional, fully actuated designs where every single joint needs its own motor. Think about it. A single string can be routed cleverly to influence multiple joints, creating a coordinated movement with just one single motor pull. And another neat aspect, the strategic use of strings and maybe some springs in the routing, introduces a natural compliance, a kind of softness into the hand. Our hands aren't rigid blocks, right? They can form. This compliance is invaluable for adaptive grasping, especially when dealing with irregularly shaped objects or unexpected contact. The springs and strings can passively conform, absorbing some impact, ensuring a more stable grip without needing complex active feedback control loops for every single joint. And the tensioning itself, that's all handled externally by servo motors or maybe some kind of reels on that control board. This further simplifies the hand's structure, making it easier to build, easier to repair, easier to maintain. This foundational design decision tackles complexity right at the hardware level, paving the way for a more practical robot hand.
Okay, that mechanical layer sounds incredibly clever. Lightweight, compliant, fewer parts in the hand itself. But then the next layer, the coordination layer. This is where it gets really ingenious, I think. Instead of trying to control each of those external strings individually, which, let's face it, would still be incredibly complex to program the system, uses what's called a synergy-based approach. And it's deeply informed by how our fingers naturally coordinate their movements. Think about it. You don't consciously command each of the, 14 joints in your fingers separately when you pick up a coffee cup. No, your thumb and index finger just naturally work together for a precision grip, like picking up a coin. And your middle ring and pinky fingers automatically group together for a power grasp, like holding a hammer or that soda can. This layer essentially builds that natural coordination right into the control system.
Precisely. This coordination layer directly and quite profoundly addresses that actuator complexity issue by consolidating control. It introduces something called a synergy matrix. You can think of it as a mathematical blueprint or translator. Instead of needing a separate control signal for every single string or every degree of freedom, this matrix acts as an intelligent intermediary. It maps higher level, more abstract commands, things like increase grasp strength a bit or start rotating the object to the precise low-level string tensions needed. But crucially, it applies these tensions not to individual strings in isolation, but to predefined groups of strings. Groups that are designed to move together in a coordinated way, mirroring those biological synergies we just talked about. It's mimicking the brain's own motor control strategies, where maybe one single neural signal activates a whole pattern of coordinated muscle movements, not just one fiber. And research, like the work by Klein and Vanderhelm, really emphasizes this. It not only dramatically reduces the required number of actuators, you might get a wide range of grasps with maybe just 2 to 4 independent control signals, but it also promotes smoother, more lifelike motion. Because the movements are intrinsically coordinated from the start, rather than being pieced together from lots of independent, potentially jerky joint movements, it's a really fundamental shift in how you think about robotic control. You move away from micromanaging every tiny detail, and instead embrace this macro-level pattern-based approach. So by implementing this synergy matrix, the system can achieve a broad range of useful hand postures and grasping capabilities, but with significantly fewer motors than a direct joint-by-joint control scheme would ever need. It's like finding an elegant cheat code for complexity, embedding that human-like coordination directly into the control architecture.
Wow, okay. Synergy Matrix maps high-level intent to coordinated string groups, fewer motors needed, smoother motion. That makes sense. So what does this all mean then for the intelligence of the hand, its ability to maybe learn new things, adapt to different objects? This brings us to the top layer, right? The control layer. And this is where you said the machine learning magic really happens, kind of bringing the whole system to life. It uses manifold learning, specifically a technique you mentioned called unsupervised kernel regression, or UKR, to compress all that incredibly complex data from human hand demonstrations into a much simpler, low-dimensional latent space. So this latent space.
Okay.
It's like a simplified map, maybe just 2D or 3D. And each point on this map doesn't just represent one joint angle, but an entire complex hand posture. Is that the idea?
That's exactly the idea. And this is another crucial mechanism for reducing actuator complexity, maybe the most abstract, but equally powerful. Instead of the robot or its controller needing to explicitly figure out and command dozens of individual joint angles or string tensions, which would be this unwieldy high-dimensional control nightmare, it operates entirely within this incredibly compact, low-dimensional latent space. Think about human demonstrations of tasks, like smoothly turning a doorknob or carefully lifting a fragile glass. Initially, that's very high-dimensional data, right? Continuous changes across many, many joints over time. But through manifold learning, these complex movements get represented as smooth, continuous curves or points within this much simpler latent space. And the benefits here are really significant. First, it allows for robust generalization. The robot can adapt to variations in objects or tasks it hasn't explicitly seen during training, just by moving to a nearby point on the map. Second, it provides an extraordinarily compact representation of these complex sensory-motor patterns. This makes storing the data and processing it much more efficient. And third, it enables efficient, smooth interpolation between known movements. So, moving smoothly on the map results in smooth, natural-looking motion of the hand. So during actual use, the robot, or maybe a human using a joystick, simply selects a point or traces a path in this simplified latent space. The learned UKR decoder then automatically produces the corresponding high-level synergy commands needed for that posture or movement. And those commands get passed down to the coordination layer, the synergy matrix, which figures out the string tensions. In essence, this translates a highly complex, multi-joint control problem into the much more intuitive act of just navigating a simple 2D or 3D map. This dramatically reduces the number of direct control variables the system needs to actively manage, abstracting away the need to command individual actuators one by one. It's a remarkable way to manage inherent complexity by finding the hidden simplicity within it.
Okay, stepping back for just a second though. You might still wonder if the hand has so many joints, so many degrees of freedom, why do we only need this low dimensional space like 2D or 3D to control it effectively? It still feels a bit counterintuitive. Surely you'd lose versatility.
Yeah, it does seem counterintuitive at first, but the neuroscience actually gives us a really key insight here, and it's pretty profound. Despite the human hand having, over 20 individual degrees of freedom, all the ways its joints can bend and twist our actual grasping behaviors, the things we do every day occupy only a surprisingly narrow, lower dimensional slice of that vast potential movement space. Think of it like this. While your hand could theoretically contort into millions of bizarre, physically possible shapes, it really only ever uses a specific, much smaller subset of those shapes for functional tasks, like grasping, pinching, pointing, etc. Seminal studies, like the work by Santello and colleagues back in '98, and consistently confirmed since then, show that a surprisingly small number of these coordinated patterns, what they call postural synergies, can account for the vast majority, maybe 80–90% of the hand-shape variability during natural everyday movements. This strongly implies that there's an underlying smooth, low-dimensional surface that's our manifold, where most natural, useful human-like hand movements actually occur. And so for the Marionette Paradox system, this insight is applied directly. They compress that full hand pose data, which starts out very high dimensional, into a latent vector of maybe just 2 or 3 dimensions. And this drastic reduction works, it's effective, precisely because it mirrors how our own brains seem to simplify and organize motor control by leveraging these underlying synergies and patterns.
Right, okay, so the useful movements live in a smaller space. Now, you mentioned there are many ways to compress data, PCA, autoencoders, but this thesis specifically chooses unsupervised kernel regression, UKR. Why UKR? What makes it better than simpler methods, or maybe even more complex deep learning models for this specific job?
That's a really crucial question. And the answer really boils down to the quality of the inverse mapping and the smoothness that UKR provides. While other methods, they can compress data effectively, UKR really excels because it offers both high reconstruction accuracy, meaning it can faithfully recreate the original complex hand pose from that compressed latent point, and critically for robotics, it ensures smooth, continuous transitions across similar input values in that latent space. For a robot, this smoothness is absolutely vital for practical, real-world use. Imagine you're controlling the hand with a joystick in that 2D latent space. If you make a tiny, smooth movement with the joystick, you need the robot hand to respond with a similarly tiny, smooth change in posture. You don't want it suddenly jumping or jerking between poses. UKR helps guarantee that predictability. Work by researchers like Stolp and Skull back in 2013 really demonstrated how UKR allows for this fluid navigation between different learned behaviors, and it generalizes remarkably well to movements the system might not have explicitly seen during its training phase. That's a big advantage over just, say, a simple lookup table. So, in the context of this thesis, UKR is trained on a carefully collected data set of reference grasps. It essentially learns the complex mapping from those low-dimensional latent points to the high-dimensional hand postures. This creates a powerful latent-to-tendon transformation. What that means in practice is a simple low-dimensional input from that latent space translates directly and smoothly into an expressive multi-digit posture. And that posture command is then seamlessly routed through the synergy matrix to control the precise string tensions in the physical hand. It creates this elegant, smooth pipeline from abstract intent to physical action, making the robot's movements predictable and graceful.
It's quite an image, isn't it? Controlling this incredibly complex robotic hand just by moving a joystick around in 2 dimensions. Or maybe even just gesturing with your own hand and having the robot mirror the posture smoothly. That's the power and the intuitive appeal of this low-dimensional latent space. A 2D space, for instance, it provides this incredibly intuitive interface. It lets a user navigate this vast landscape of possible grasps and hand shapes just by adjusting 2 continuous variables, like moving a point on an XY plane. It seems to make interacting with something very complex feel surprisingly accessible, even if you're not a robotics expert.
Precisely. Each single point in that simplified, low-dimensional space corresponds to a complete, complex, high-dimensional hand pose, which is then decoded through that sophisticated UKR model we just discussed. This approach dramatically reduces the complexity for the user, whether it's a human operator or even an autonomous planning algorithm. They don't need to think about commanding dozens of individual joint angles. It also simplifies the underlying control algorithms themselves because they're operating on a much smaller, more manageable set of variables. And what's really neat, and a major practical advantage, is that the system is designed to be highly extensible. So if you want the hand to learn a new task, grasp a new type of object, or perform a new gesture, you don't necessarily need to redesign the entire mechanical system or rewrite all the software from scratch. Instead, you can often just collect some additional human demonstration poses relevant to that new task, and then retrain or maybe just fine-tune the existing UKR model. This fits perfectly with the modern direction of adaptive, data-driven robotics, where systems are designed to learn and evolve over time without requiring extensive, costly re-engineering for every new capability you want to add.
Okay, that sounds incredibly powerful and flexible. But of course, no design is perfect. Every elegant solution usually comes with some trade-offs or challenges. What are the limitations? What's the sort of fine print of this manifold-based control approach that engineers or researchers need to keep in mind?
That's a very important consideration, absolutely. And the main concerns, really, as with almost any data-driven approach, tend to revolve around two key things: coverage and potential manifold folding. So coverage basically refers to whether the initial training data, the human demonstrations used to build that UKR map, adequately represents all the useful or natural grasps the hand might need to perform in the real world. If the system hasn't seen a particular type of grip during training, then trying to interpolate into those unrepresented regions of the latent space might lead to movements that are unnatural, maybe inefficient, or possibly even just ineffective for the task. It's like trying to find a specific small street using a map that only shows major highways. You can get close, but the fine details might be missing if they weren't on the original map. Secondly, there's this potential issue of manifold folding. Imagine trying to use a map that's been badly crumpled up. Two streets that are actually far apart in the real city might appear right next to each other on the crumpled map, right? Manifold folding is kind of similar in our latent space. It's possible that two very distinct, physically different hand poses in the high-dimensional joint space could inadvertently get mapped too closely together in the compressed, low-dimensional latent space during the learning process. This could potentially cause ambiguous control signals. A small intended change in the latent space might suddenly lead to an unintended, large, or even jerky change in the actual hand posture, which would obviously be terrible if the robot is trying to carefully pick up a delicate object. However, these challenges, they aren't insurmountable. They're mitigated in the thesis and in practice by very careful data curation, making sure you have a diverse and representative set of training examples, and by enforcing smoothness constraints during the UKR model training itself. This helps to balance the flexibility you want with the coherence you need, preventing those abrupt, unwanted transitions. It's really about designing the map carefully to avoid these potential pitfalls.
Got it. So careful training data is key. Now let's circle back to synergies. You've mentioned them a few times. This idea isn't just some clever engineering trick or a neat theoretical concept, is it? You said it's deeply rooted in how our own brains actually control our hands. I mean, you rarely, if ever, move just one single finger joint completely independently of all the others, right? There's always this inherent, almost subconscious coordination in pretty much everything we do with our hands, whether it's typing, gesturing, or grabbing something.
That's absolutely right. Studies in neuroscience, including that seminal work by Santello we mentioned, and extensive reviews by people like Klein and Vanderhelm, they consistently show that when we grasp things, humans activate these motor synergies. These are essentially coordinated patterns of muscle co-activation. They dramatically reduce the number of independent control signals the brain actually needs to generate. Instead of having to meticulously command each of the dozens of muscles and joints involved in the hand, our brain seems to issue these higher-level commands that activate pre-programmed, efficient patterns. It turns out that a surprisingly small handful of these basic patterns can explain the vast majority of the variability we see in everyday grasping motions. So instead of individual joint commands, the brain appears to blend these fundamental motions together, which simplifies the whole control process incredibly significantly. It's a truly brilliant biological solution to managing a very high-dimensional control problem, one that evolution has clearly refined over millennia.
So the logic follows. If our brains do it this way, using these efficient shortcuts, why shouldn't robots? This powerful biological wisdom has directly inspired this new wave of robotic hand design, hasn't it? Moving away from that brute force, one motor per joint idea and embracing a more bio-inspired synergistic approach.
Exactly. And this is where it gets really transformative for robotics. Hands designed with these biological synergies in mind, like the well-known PSI-AT soft hand. For example, they can achieve incredibly complex adaptive grasps, using far fewer actuators than traditional designs. For instance, the soft hand can control its entire hand, achieve really complex grasps, using as little as one or maybe two motors. It does this through cleverly routed elastic tendons and shared mechanical structures that inherently create coordinated movements, rather than needing a separate motor for every single joint. This approach drastically reduces the hardware requirements, the weight, the cost, while simultaneously promoting smoother, more naturalistic motion that can passively adapt to the shape of the object being grasped. If you push on one part of the soft hand, the whole hand tends to flex and conform in a coordinated way, much like a human hand, rather than just that one point being rigid. Research confirms that synergy-based control not only minimizes the actuator count, but also significantly improves a robot's ability to generalize its skills to new, previously unseen tasks. Why? Because the embedded coordination patterns inherently reflect human motor strategies, making them robust and versatile for the kinds of tasks humans do. And this exact principle is directly and powerfully applied in the marionette hand, designed to achieve that dramatic reduction in actuator complexity, going from potentially dozens of motors down to maybe just a handful.
Okay, so we have the low-dimensional latent space representing the desired pose, and we have the idea of synergies coordinating groups of joints. But how do those abstract low-dimensional inputs from the manifold layer actually translate into physical hand movement using these synergies? What's the mechanism linking the map to the muscles, or in this case, the strings?
Right. That's the crucial connection point for understanding the whole system flow. And the synergy matrix we introduced earlier, that is the critical link in this entire process. It's not just a concept. It's a tangible mathematical transformation implemented in the control software. It takes those low-dimensional outputs coming from the learned latent space, which remember represents a desired full hand posture, and it maps them onto a specific set of tendon tension values. The precise amount of pull needed for each of the marionette hand strings. So instead of needing to manually figure out and control each individual string or tendon, this matrix automatically calculates exactly how much tension each string should receive. And this calculation is based on just a small number of abstract, high-level inputs derived from the latent space, perhaps representing a pinch command, or a curl command, or a blend between them. Now, these patterns aren't arbitrary. They are deeply inspired by common functional human grasps, like the power grip for holding a tool, the precision grip for picking up small things, the lateral pinch for turning a key. By allowing for smooth, continuous blending between these fundamental patterns, the system can produce a huge variety of nuance and intermediate hand motions. For instance, a small change in the pinch input might suddenly adjust the tension across several different strings simultaneously to refine the grip precisely, rather than needing to command each individual string separately. Critically, this synergy matrix is the direct mechanism by which the control of the actuators is profoundly simplified. It reduces a high-dimensional control headache down to activating and blending just a few coordinated patterns. It's effectively the brain's blueprint for efficient motor control translated into a robotic command structure.
And the marionette mechanism itself, the physical strings and external actuators, that plays a huge role here too, doesn't it? It's not just a catchy name for the thesis. It feels like a fundamental design choice that directly enables this synergistic control and simplicity.
Absolutely. It's integral to the whole concept. Unlike many traditional robotic hands where the motors are embedded right inside the hand structure, or even worse, inside individual fingers, which creates all sorts of problems with bulk, heat dissipation, wiring complexity, this system uses those external tension cables. The strings are carefully routed through guides to specific attachment points on the fingers, mimicking tendon insertions, and then the tension, the pulling force, is applied from that central off-board mechanism. This external system can pull on multiple strings simultaneously, controlled by the outputs of the synergy matrix, perfectly mimicking how a puppeteer pulls strings to create coordinated movements. This externalization is a direct and powerful contributor to reducing actuator complexity simply by centralizing the driving force. It means the hand itself can remain incredibly light, very compact, and highly modular. This makes it simpler to fabricate, easier to maintain, and potentially much more adaptable or repairable. Think about the engineering benefits. A single motion command coming down from the control layer, filtered through the synergy matrix, can result in perfectly coordinated tension across multiple tendons without needing separate dedicated motors for each and every one located in the hand. This significantly reduces the internal torque requirements within the hand structure itself, minimizes the need for cooling systems, since the heat-generating motors are external, and drastically simplifies the electronic complexity embedded within the hand. Reports, like that NASA one we mentioned, specifically support this trend, towards externally routed systems, especially for applications like space robotics or advanced prosthetics, where minimizing the mass and complexity within the hand itself is absolutely crucial. Every gram counts in those scenarios. It's a fantastic example of how intelligent mechanical design can solve problems that might otherwise require very complex electronics and software solutions.
Okay, so let's try and visualize the whole thing working together in real time. We have the manifold learned latent space providing that high-level abstract intent, like, I want to form a pinch grip. Then the synergy matrix translates that intent into coordinated patterns of tension for specific groups of strings. And finally, the marionette mechanics, the physical strings pulled by external motors, enact those patterns to shape the hand. How does this all flow together to create smooth, real-time control and practical motion?
Yeah, it's designed to be a remarkably fluid and elegant process, really bringing that paradox of simple control for complex action to life. Imagine you, as the operator, or maybe a higher-level autonomous algorithm, are navigating that low-dimensional latent space. Perhaps you're moving a joystick to select the desired grip shape, or the system is getting visual input about an object it needs to grasp. As that input changes in the latent space, the system rapidly decodes that abstract input into a target full hand shape. This decoding happens almost instantaneously thanks to the efficiency of that pre-trained UKR model. Immediately following that decoding, the synergy matrix takes that target shape and determines precisely how to distribute the necessary tension across all the relevant marionette strings to actually achieve that shape physically. Because this entire pipeline, from the latent space input through the UKR decoding, through the synergy matrix calculation, to the string tension output, is designed to be computationally very efficient and continuous. It enables incredibly smooth interpolation between different hand postures, and it fully supports real-time control. The real genius here, I think, is that the system itself takes care of all the intricate coordination details down at the lower levels, figuring out which strings pull how much. You, or the high-level controller, simply provide the high-level intent by navigating that simple map. The system handles the complex multi-joint execution almost automatically. And this architecture, because it's based on learning in matrices, inherently supports further learning and adaptation, making it incredibly flexible for tackling new tasks or adjusting to different environments over time. It transforms what could be a staggering computational burden into a nimble, responsive, and quite intuitive control system.
So let's bring it back to the core promise of the Marionette Paradox thesis. It really sounds like it delivers on that core idea, achieving high-dimensional complex dexterity from surprisingly simple low-dimensional control inputs. It feels like a genuine breakthrough, but what's the real, tangible impact of finding this kind of elegant simplicity?
Precisely. It fundamentally allows for expressive, complex hand motions using a minimal amount of hardware, fewer motors, simpler mechanics, and significantly reduced computational overhead compared to those traditional brute force designs. It strikes this really intelligent balance between precision and simplicity. It makes the hand capable of performing a wide array of useful tasks, manipulating tools, grasping delicate or oddly shaped objects without needing constellations of expensive, heavy, and often fragile embedded sensors, or requiring the painstaking brute force programming of every single joint's trajectory. By mimicking how human hands naturally coordinate finger motion through those underlying synergies, and then representing those coordinated motions efficiently in a simplified latent space, it intrinsically simplifies both the hardware requirements and the software control complexity. And importantly, this simplification doesn't seem to come at a huge cost to capability, at least for many tasks. It manages to preserve a wide, practical range of manipulation capabilities. It's a powerful testament, I think, to the designing for intelligence through inherent simplicity, demonstrating that sometimes the most sophisticated solutions are the ones that appear the simplest on the surface.
Now, you mentioned this thesis focuses primarily on the theoretical design, the foundational principles. But if we were to build this and test it in the real world, how would we actually go about evaluating it? What specific criteria would we use to really gauge its success against other robotic hands?
That's a key question for any new robotic system. Typically, robotic hands are judged by a fairly standard set of criteria. Things like their overall dexterity, how many different things can they do, their adaptability, how well do they handle different object shapes and sizes or unexpected situations, their hardware complexity and cost, how easy and cheap are they to build and maintain, and the ease with which they can be controlled. Is it intuitive for a human or an AI? This thesis, however, strategically optimizes for a slightly different, maybe more focused set of metrics. The key ones here seem to be expressiveness, which means the ability to produce a wide range of recognizable functional grasps that look natural. Then efficiency, requiring those low-dimensional inputs to generate complex motions. And finally, elegance, really emphasizing that mechanical and computational simplicity. The theoretical foundation, drawing heavily on prior work in manifold learning and synergies, suggests that the combination of UKR and synergy-based control would enable very smooth, biomechanically plausible transitions between different hand poses. If implemented physically, we could reasonably expect it to effectively execute maybe 6 to 10 core grasps that are crucial for common manipulation tasks. Things like the cylindrical grasp, holding a bottle, the tripod pinch like holding a pen, a hook grasp carrying a bag, a spherical grasp holding a ball, and the lateral pinch like turning a key. These are all essential for practical applications in service robotics or for assistive devices, as research by people like Phoenix has shown. So success wouldn't just be measured by how many grasps it can do, but how naturally, efficiently, and reliably it can perform those key functional ones using its simplified control.
It really does sound incredibly practical for actually building physical hands, not just modeling them in simulation. That focus on simplicity seems like it would have a direct, tangible benefit in terms of manufacturing, cost, and maybe even robustness.
Indeed, that inherent hardware efficiency is arguably one of its major strengths, making it highly practical. Instead of the conventional wisdom demanding one motor per degree of freedom, maybe embedded right inside the hand, this system demonstrates that potentially as few as 2 or 3 external motors could generate sophisticated, full hand motion, just by precisely routing tension through that synergy matrix system. This approach closely mirrors the success seen in other adaptive grippers, like that Pizai soft hand we talked about, and it also aligns perfectly with the direction NASA is taking with some of their under-actuated hands for planetary exploration, where, again, minimizing mass, complexity, and potential points of failure inside the hand is absolutely paramount. The external tendon routing offers multiple concrete benefits. It drastically reduces the internal torque requirements within the hand structure itself, which means smaller, lighter components. It minimizes cooling needs because the main heat source, the motors, are external. And it significantly simplifies the electronic complexity that needs to be embedded in the hand itself. Furthermore, the inherent modularity of this kind of design is a huge advantage. Components, fingers, strings, even the external actuator board could potentially be easily swapped or upgraded without needing to scrap the entire system. This makes it an ideal platform for educational purposes, for rapid research prototyping where you want to iterate quickly, and potentially for highly cost-effective deployments in various applications where traditional complex robotic hands are just prohibitively expensive or too delicate for the environment.
Okay, but as we discussed, every elegant solution has its challenges. No free lunch in engineering, right? What are the current limitations acknowledged in this design? Where would further development or improvement be needed to really push this from a compelling thesis to a widely applicable technology?
Right. Acknowledging limitations is crucial for progress. And the current theoretical design, as presented, does have a few key areas that offer clear pathways for future work. Firstly, as we touched upon briefly, it primarily operates in an open-loop fashion. This means it currently lacks active, real-time force feedback. There aren't sensors on the fingertips telling the controller how hard it's pressing, or sensors measuring the tension in the strings directly, or torque sensors at the joints. Without this feedback, the hand can't adaptively regulate its grip strength on the fly or detect if an object is starting to slip from its grasp. It's essentially relying solely on those pre-computed mappings from the UKR model. Imagine trying to pick up an egg versus a rock without force feedback. The hand wouldn't inherently know to apply different amounts of force. Secondly, the grasp diversity, the total range of different hand postures and manipulations they can achieve, is inherently constrained by the quality and, importantly, the quantity of the training data used to create that UKR manifold map in the first place. If the training data didn't include examples of, say, holding a very specific or unusual tool, the system might struggle to generate that particular grasp optimally, or at all. It's limited by what has been shown. And as Klein and Vanderhelm pointed out, while you can increase the number of synergies modeled to potentially expand the hand's expressiveness, doing so also inevitably introduces additional complexity, both in the training process for the manifold and potentially in the mechanical routing of the strings. So there's a trade-off there between expressiveness and maintaining that core simplicity, which needs careful consideration depending on the application.
Right, those are important considerations. But it definitely doesn't sound like the end of the story for the Marionette Paradox, does it? This really feels like a powerful foundation, a strong starting point that clearly lays out a path forward. So where could this marionette hand concept go next? What are some of the exciting pathways for future work that this architecture unlocks?
Oh, absolutely. This architecture provides a really clear and compelling blueprint for some remarkable future work, potentially expanding its capabilities significantly. I think the immediate and probably most crucial next steps involve building and testing a physical prototype. This could likely be done using affordable techniques like 3D printing for the hand structure, combined with low-cost cable components and readily available external servo motors. Building a physical version is essential for empirical validation, seeing how the theoretical models actually perform in the messy real world. We would allow researchers to uncover practical challenges that might not be obvious in simulation, things like friction in the cable guides, potential material fatigue over time, or the real-world dynamics of string tensioning. Another absolutely vital pathway is the integration of tactile and force feedback to enable closed-loop control. This means adding sensors, maybe simple pressure sensors on the fingertips, to detect contact and measure grip force, perhaps tension sensors along the cables themselves to monitor the pulling force, or even miniature IMUs, inertial measurement units, within the fingers to get more detailed motion feedback. These sensors would allow the hand to react dynamically to its environment. For example, it could automatically adjust its grip strength in real time to avoid crushing a delicate object it picks up, or it could sense if an object starts to slip and instinctively tighten its grip. This moves the system beyond just executing pre-programmed motions towards intelligently interacting with its surroundings. We could also see significantly expanded synergy modeling, maybe moving beyond just the most common canonical grasp by learning synergy patterns directly from real human hand data captured using advanced motion capture systems. Or perhaps applying statistical techniques like principal component analysis to even larger data sets of human motion to uncover more subtle, nuanced coordination patterns that represent a wider range of dexterous actions. And looking further ahead, there are really exciting possibilities in developing multimodal interfaces for controlling the hand. Imagine the hand being controlled not just by a simple joystick, but perhaps by a vision system that recognizes objects and automatically predicts the optimal grasp posture from the latent space based on the object's shape and size. Or, particularly relevant for advanced prosthetics, direct control via electromyographic (EMG) signals read from muscle activations on a human user's residual limb. Even brain-computer interfaces could, in theory, eventually map a user's direct intention to specific positions or trajectories within that latent space, offering potentially unprecedented levels of intuitive control. And finally, investing in high-fidelity simulations using modern robotics platforms would allow for much more rapid iteration and testing of new synergy mappings, new control algorithms, even exploring advanced machine learning techniques like reinforcement learning. You could potentially have the simulated hand autonomously practice and refine its manipulation skills in a virtual world millions of times before ever deploying it on physical hardware. The potential for creating a more intuitive, adaptable, and robust robot hand based on these principles is really immense.
It really paints a picture of not just building better robots, but maybe reaching into other areas too. This system feels like it has a broader significance, perhaps for education, accessibility, or even just changing how we think about tackling complex engineering problems in general.
I think that's right. If we connect this to the bigger picture, definitely. Given its intentionally low cost and its transparent modular architecture, this system holds, I think, immense potential for STEM education, right from K-12 up through university levels. It offers a really tangible, hands-on way for students to learn about complex, interdisciplinary topics like biomechanics, control theory, machine learning, even the philosophy of robotics, by actually building, programming, and experimenting with a real, albeit simplified, robotic hand. That's powerful learning. It could also significantly advance research into more accessible prosthetics, particularly for resource-constrained environments or maybe lower-income regions, where the cost of current high-tech prosthetic hands is often a major barrier. This approach could help democratize access to advanced manipulation capabilities. And maybe on a more philosophical level, this project really invites us as engineers and designers to actively explore those fundamental trade-offs between efficiency, precise control, and achieving human-like performance in a very tangible and accessible way. It's a great case study in building smarter, not just bigger or more complex, and finding genuine elegance in tackling difficult engineering challenges.
What a fascinating deep dive. We've really unpacked the Marionette Paradox thesis today. We explored how it so brilliantly integrates those marionette-inspired mechanics, the profound wisdom drawn from human digit synergies, and the computational power unlocked by manifold learning. It really stands as a powerful testament, doesn't it, to achieving incredibly complex dexterity through thoughtful simplification and intelligent design, rather than just relying on brute force engineering and adding endless resource-intensive complexity. The paradox of simplicity enabling sophistication truly seems to shine through here.
I agree. And at a time when robotics, let's be honest, often leans towards ever higher cost, higher complexity solutions, often trying to replicate biological complexity with even greater mechanical and computational complexity, this project offers a really compelling counter-narrative. It serves as a potent reminder that the human hand, which is arguably our most intricate and versatile tool, achieves its profound complexity and its incredible range of motion, not through brute force, but through elegant underlying patterns. Through the inherent wisdom of synergies in motion, through adaptive feedback loops, and through continuous learning and adaptation over our lifetimes. This work encourages us, I think, to build machines not just to merely imitate the superficial structure of the hand, but to truly understand and embody its inherent wisdom, its underlying principles of efficient and adaptable movement. It's a rather profound thought when you dwell on it. The marionette, which we traditionally think of as a symbol of strict external control, here becomes a metaphor for grace found within constraint. A machine that moves with a kind of human wisdom, encoded in every string, every tension, every learned pattern derived from observation. It leaves you wondering, what new possibilities might truly emerge when simplicity, inspired by the elegance of nature itself, becomes the ultimate guiding design principle in robotics? Could it enable capabilities that we previously thought were out of reach simply because we assumed complexity was the only answer?